So very good evening. So myself, I am Anand. So I am currently working here as a assistant professor in research. So today I am going to demonstrate on the XPS system. So before going into the system, just I am going to give the pinch of the XPS instrumentation part. So how it works and what are the components are involving in XPS system. So here we are using the aluminum K alpha target. So aluminum K alpha source. In generally there are two types of anodes are there. One is the aluminum K alpha source, another one is the magnesium source, and few dual system is also available. But here in from thermoscientifics we have the single anode system. It's a aluminum K alpha. So in order to generate these X-rays, here we have the lab 6 emitter. So generally they may use the thermionic emitter. Here we are using the lab 6 emitter. So this lab 6 emitter will emit the high energy electrons. These high energy electrons are going to interact with the aluminum target. So once it's impinged onto the aluminum target, it generates X-rays. While generating these X-rays, there are mixture of wavelengths are produced. So that might be a K alpha 1 or K beta and K alpha 2 and etc. So but we need the monochromatized wavelength. So for that, here we are using the monocrystals. So here we have the quartz monocrystal. These monocrystals work as a Bragg's diffraction. Like the XRD, here the monocrystals, the range of radiations will be diffracted and it will allow only on the K alpha 1. This K alpha 1 lines monochromatized wavelength, it's going to interact on your samples. So here we are using the here the photoelectrons are generated based on the principle of photoelectric effect. So we are allowing the external energy. This energy is sufficient to remove the core level electrons. So this core level electrons is nothing but it's the photoelectrons. So once the photoelectrons are generated, these electrons are going through the electron transfer lens. So this generator electrons will be spreaded out into the chamber, but we needed to converge and we have to direct into the detector. So for that, here we are using the electron transfer lens. This electron transfer lens converges the electron beam. This then it will allow to the hemispherical analyzer. So hemispherical analyzer, it consists of two components. One is the inner hemispherical analyzer, another one is the upper hemispherical analyzer. So in this hemispherical analyzer, we will allow the particular energy. For examples, if you are allowing 200 eV, so if the ejected photoelectrons having 200 and above, it will be collide to the upper hemispherical analyzer, and if it's lesser than 200 eV, it will be attracted into the inner hemispherical analyzer. So the particular energy will be transferred to reach the detector, and the detector will detector will receive the photoelectrons and it will measure the kinetic energy of the photoelectrons. Then due to the computerized, this kinetic energy will be converted into binding energy scale and we are getting the binding energy. So the binding energy is the fingerprint, and from this binding energy scale we can find the chemical information like what is the chemical composition of the material and oxidation state. So in this XPS system we are getting three major information. So first one is what are the elements are presented in your samples, whether it's known or unknown. What are the elements are presented in your samples that will be identified from the survey spectrum from 0 to 1486 eV. Then after that we have to do the high resolution spectrum for the each elements. Then from this high resolution spectra you will get the chemical composition. So for examples, if your materials has the titanium, this titanium may reacted with the oxygen like titanium oxide. Okay, so TiO2. So how to confirm whether it's fully converted into TiO2 or it's in the pure form of Ti. So when we do the XPS system, so you will get the different binding energy scale. So when you check with the binding energy scale, where that is corresponds to titanium, the zero oxidation state. If the titanium reacted with oxygen, it will form the titanium oxide. Their binding energy scale either shifted to higher angle or lower angle. So like that, when the metals are become the any compound, their binding energy scale will be different. So binding energy is the fingerprint which gives the chemical composition of the materials. And the second, which oxidation state, either it's titanium, it's 0 oxidation state, or the titanium is 2 plus or 3 plus, which oxidation state, this will, based on this oxidation state, the peak will be shifted. So from this XPS system, we will get what are the elements are presented and the chemical composition of the material and oxidation state. So in this work function, we also have the flood gun. So and we also have the ion gun. So the purpose of this flood gun, for the insulating samples, and we are allowing the photoelectrons, and we are keep on removing the electrons from the materials. So the for the insulating samples, the electrons will be very less. So the charge will be accumulated more in the insulating samples. So in order to compensate this charging effect, we are allowing the free electrons into the samples. So it will, in order to neutralize the samples, we are using the flood gun options. And this XPS is a surface phenomena, and it shows surface sensitive techniques. So for example, here you have the bulk materials, and the thickness of this material in few mm or few micrometer. But here is so surface sensitive technique, you will get the information onto the few tenth of nanometer or 10 nanometer of informations. These X-rays can penetrate more than that, like few microns it can go. But while coming out, this will collide with the neighbor, the ejected photoelectrons will be collided with the neighbor's atom, and it loses their energy. So once it's come out from the samples, when we analyzed the photoelectrons, their energy, the energy already it loses, so we will not get the exact binding energy scale. So we are concentrating only on the top 10 nanometer. There will not be any collisions, and we can accurately measure the binding energy scale of the system. Suppose in this bulk materials, if you are very much interested in the depth profile, so you want to perform more than 10 nanometers, so what we can do, we have the ion gun options. So ion gun, here we are using the argon ion. So this argon ion will impact on your samples, and it will remove. It will remove the few nanometer thickness, then you can perform XPS. So for examples, if your sample thickness it's around 20 nanometer, it's so surface sensitive, you will get only the top 10 nanometer informations. So if you want to perform, if you want to check what is the chemistry beyond 10 nanometers, you need to do the argon etching option. It's a depth profile analysis. So how much depth you can go, you can remove the argon clusters with the help of argon cluster. You can remove the layer by layer, then you can perform XPS. So, but you have to very careful in selecting the ionization energy. If you are giving more ionization energy, it will damage your samples. So you have to give the very minimum energy to remove the sample surface. But this is not applicable for the bulk like powder samples. If your samples are thin film or bulk samples, you can do etching, and you can do the any depth profile analysis in order to study the depth information of your materials. So up to few nanometer, you can perform the XPS, and you can study the chemistry of your materials in the more than 10 nanometer informations. So now we will go to the instrumentation part. So here, so this is the thermoscientific from K alpha model, and this XPS system not only on the XPS, here we also have the UPS options. So in XPS we will use the X-ray source. In UPS we are using the ultraviolet radiation. So the X-rays, their energy is higher, So it can go deeper into that and it will remove the K cell electrons. But in UPS, we are using the ultraviolet radiation. Their energy is very lesser, like around 21 eV. So this 21 eV could not go more than that. So, but it can remove the valence band electrons. So from this valence band removal, we can calculate the work function of the materials. So in order to study the chemical composition, we can perform the XPS. If you want to study the work function of the material or the valence band informations, you can perform the UPS analysis. So this is the sample holder. This XPS system will consist of two chambers. I will explain here. So this is the schematic of this XPS system. So this XPS system has two chamber. One is the load lock chamber. So this is the load lock chamber. So here we are mounting our samples. Okay. Then this load lock chamber are isolated by the isolation wall, and we have the analysis chamber. So we are not going to disturb this analysis chamber because we need to keep the ultra high vacuums. So for that, while loading your samples or unloading, we will use only on the load lock chamber. Okay. So here we are using two turbo pumps to keep on achieve the ultra high vacuum in the systems. So now, so this is the sample holder. This is the sample holder what I have loaded in the samples. So this is the sample dimension. So maximum of 60 mm cross 60 mm. So we can accommodate the samples. Okay. So here the sample dimension could be 2 mm to the maximum of 20 mm cross 20 mm can be mounted onto the sample stage. So here we have different sample holder for different samples type. For examples, if you have the powder samples, we have the powder sample holder. If you have the any thin film samples or bulk samples, we have the different sample holder. And if you have any fiber kind of samples, we have the fiber samples holder. And if you want to perform any air sensitive material or environmental sensitive material or any battery kind of things, we have the separate vacuum model. So you can mount your samples in the globe box itself. Without breaking the vacuum, you can transfer your model into the system and you can perform the XPS. So these kind of advantages are available in these features. So here I have loaded the standard BAT samples in A slot, and the aluminum foils also loaded in the system for the demonstration purpose. So here the samples are in the load lock chamber. So now I am going to transfer the samples to the analysis chamber. Before transferring the samples, we need to check the vacuum pressures. So the vacuum pressure should be 10 power minus 7, and it should be in 10 power minus 7, then only we can transfer the model. So now the range of 10 power minus 6, so we need to wait for a while to transfer the systems. So here in XPS system, we are having different kind of gases. So one is the nitrogen gas. So one is the nitrogen gas. So nitrogen, the purpose of this nitrogen gas for the venting purpose. Suppose if you want to, while removing or the loading your samples, you have to use the for the air molecules will, the environmental air will not be entered into the sample holders. For that we are using the nitrogen gases, and the argon gas for the sputtering purpose, and then helium gas for the UV sources. So in order to generate this UV light, we are using the helium sources. So now you can see the sample, it's transferring through this wall, and it will be fixed in the analysis chamber. Okay. So there is a arm, the robotic. So the sample holder will be moved to the analysis chamber. So once it's moved, the valve will be closed and it will reach the maximum vacuum. So now you can see. So before it was in the low lock chamber, now the samples moved to the analysis chamber. So here it's a micro focused beam, and here you can focus which area you want to perform. So this is the BET transparent samples. We are moving to the particular area. Here we are creating the new experiments. So here we need to focus the area. So this here we have the optical view. You can focus which area you want to perform. So once you manually focus the particular area, then you have to generate the gun. So for that, I will turn on the X-ray gun, and this X-ray gun has the spot size. So here we are generating the X-rays, and the X-ray spot will be transferred onto your samples. So here the spot size you have to fix manually how much spot size you required. So in generally we will use the maximum spot size of around 400 micrometer. And here it will ask whether you need the flood gun. For the insulating samples, we must apply the flood gun. For the conducting samples, if it's okay, you can apply. But for all the conducting or semiconducting or the insulating samples, we can apply the flood gun. So then you have to create the point. So once you selected the point where you are going to analyze your samples, then you have to select which spectrum you want to collect it. So whether you want to do the survey spectrum or the valence XPS or the high resolution spectrum. So like that you have to choose which spectrum you want to perform. So now I am going to select the survey spectrum. Then I run the system. So here you can see the X-ray gun is started, and this indicating that now the analysis is started. So now the flood gun is getting started. So once the flood gun is started, then the X-rays will turn it on. Here we have given, I have given the spot size of 400 micrometer. This spot size is variable. So here you can see. Suppose this is your objective area. Here you want to perform the XPS. So here you can see the bright spot and the dark spot. Suppose this bright spot, that area is very few micrometer, for a case of 80 micrometer. So in that cases, if I give 400 micrometer, the remaining area will be analyzed. So for that you can reduce the spot size. So here this thermoscientific, the spot size is variable from 50 micrometer to 400 micrometer, and you can depends on the area and depends on the particular which one you want to perform, you can reduce or increase the spot size value. So here the ranges from 50 micrometer to 400 micrometer, and the interval can be 5 micrometer intervals. another time ஆகும் அங்கே ஃபஸ்ட்டு தான். So in this chemical state, you can see the binding energy is based on the binding energy of Fe is differ, and if the oxygen is reacted with the iron, their binding energy will be shifted to the higher angle. If the oxygen is further reacting, it will become the Fe2O3, then it will be shifted to the higher angle. So this binding energy scale will confirm which composition of your materials. And the second diagram is the depth profile analysis. So in this depth profile, the argon etching will play the role, and it will remove the layer by layer, and it will perform the XPS. Suppose if you have the any multi-layer thin film, like 10 nanometer of one layer, then 10 nanometer another layer, then 2 nanometer of another layer. So the total of 22 nanometer of thickness or any multi-layer thin film you have. So you can remove every 3 nanometer of layer, then you can perform XPS. So like that, until few nanometer depth, you can do the depth profile analysis, and you can get the chemical composition of the materials. And the third diagram is the XPS analysis for the fiber samples. So this holder we have here, you can screw and you can fix the fiber material, and you can fix the spot size, and you can perform the XPS system. Another, we also have the mapping options. It's like a Raman mapping or the FESM EDX mapping. Similar to that, how the elements are distributed. So that can be mapped, and that mapped image can be generated. So like to any composite material you have, how it distributes can be mapped, and you can get the mapping images also. And these are the failure analysis for the some other applications. And this is the battery holder. So if no, the air sensitive materials can be mounted, and here this holder will be vacuum sealed, and that same this whole holder can be transferred to the load chamber. While before performing the analysis, it will be open to the analysis. So in between, we will not break, the material will not be exposed into the environment. And here we have the UPS option analysis, as well as for to identify the valence band informations. So if you are working in energy materials or any solar cell applications, they want to cross check. Like usually we will do the UV visible analysis to calculate the band gap. So here when we perform the BB XPS, you can get the valence band informations. Apart from this valence band, you can get the work function of the materials can be collected from the UPS system. And this is the snap map options for the different images, and these are the failure analysis. So from all the disciplines, from biomedical to material science and materials chemistry, corrosions, and all the kind of how the material is changes in the surface phenomena can be confirmed, and the chemical compositions can be identified in this XPS system. Conditioning. So here two all the elements can be identified from lithium to the highest element of uranium, but the hydrogen is a low ionization cross section, so hydrogen will not be identified. Hydrogen and helium will not be identified. And another one material like sulfur and iodine are volatile in nature. So these two elements containing compound, or the free sulfur or the free iodine, cannot be identified in these systems. So for that, if your material is highly stable, like for example copper sulfate, in this copper sulfate some free sulfurs are presented in your samples. If you load it into the chamber, this free sulfur will be decomposed, and it will be contaminate the chamber. So the sulfur and iodine samples are tedious, and we can't perform this sulfur and iodine samples. So you have to find any complementary technique to analyze this sulfur and iodine sample. So except sulfur and iodine samples, you can perform rest of the all kind of chemical compositions. Okay. So now the flood gun has turned on. Now the X-rays are igniting and the X-rays will turn it on. So another one options we have. So here we have the So here we have the angle resolved XPS holder. So this is the angle resolved XPS holder. Here you can mount your samples, and if you are working in ultra thin film, so in the range of 3 nanometer thin film or 5 nanometer thin film, there you want to more focus on the surface. You don't want to get the substrate information. So in that cases, you can use this angle resolved XPS. So here the angle can be tilted from 10 degree to 80 degree. So in order to tilting your angle, the surface will be more focused and you will get the more surface informations. So this is so surface phenomena up to 10 nanometer, but still if you are preparing any 2 to 3 nanometer, 5 nanometer, this ultra thin film cases, you can do the angle resolved XPS. So for that we have the separate sample holder, and this is tilting options will tilt from 10, 20, 30, so like that 10 degree interval to as a maximum of 80 degree. So now we have started the analysis. So this is a survey spectrum. So now here also we can enable the auto height options. If that is, if you want to focused area, then no need to give. But if you want to check the software itself to focus more, you can enable the auto height options. So this is the spectrum. It's collected from the PET sample. So here you can see. So this is a survey spectrum, and it collected from the range from low EV to the maximum of high EV. So once this spectrum is collected, and you can check the what are the elements are present in the samples. Here the number of scan, if you increase the number of scans, the background noise will be reduced. So here I have given the 4 number of scans for the demo purpose. So these are the peaks corresponding to different elements. So once the survey spectrum is complete, and we have the automatically identifying elements from the Avnet software, then we will perform this ESP. Then we will get what are the elements are presented. So now the survey spectrum completed. So here I did this ESP. Then PET, it's we have the carbon and oxygen. So here you will get the semi-quantitative information like how much atomic percentage. Okay. So the software itself, it will. So here you can focus. So this is the spectrum. This binding energies correspond to oxygen. So here you can see this is the oxygen, and here it will denote the S level. That means from the S orbital, these electrons are generated. Okay. So this software, when we do this ESP, automatically identifying elements, which automatically gives the background, and it's calculated the quantity of the elements. But it's a software basis, but it's not more accurate. What you have to do? You have to do the same area under the curve, and you can calculate from the high resolution spectrum. So this is the roughly the estimation, some estimated atomic percentage of the presented elements. So like that. So here this peaks corresponds to carbon 288. So this peak corresponds to oxygen 2s, and this is 1s orbital, and here we found the oxygen Auger spectrum. So that is a KL transition from the Auger informations. So these are the informations you will get from the survey spectrum. So from this survey spectrum you can conclude like our materials, it consists of carbon and oxygen, but you will not get any chemical informations. So in order to identify these chemical informations, you need to run the high resolution spectrum. For that, now forming the high resolution spectrums, now we have identified what are the elements are there. So the carbon and oxygen we need to select, and we have to run high resolution spectrum for the carbon and oxygen spectrum. So now I enable the auto hide. So here you can see it's defocus then focus. So automatically the height will be adjusted and it will focus a particular area, then it will start running the system. So now we are getting the spectrum of carbon spectrum of this PET samples. Here you can see some noises. So this noise will be reduced if you are running the n number of scans. So here I have fixed 5 number of scan. Suppose if the background noise are not perfect, you can increase the number of scans. So this is the carbon spectrum for the your materials. So when I check with the 286, this is the survey spectrum. You have one solder, then the sharp peaks, but in this high resolution spectrum you can see another one spectrum and this. So for that you need to do the high resolution spectrum in order to get the chemical composition of the materials. And here this is the spectrum of oxygen. So now the oxygen's patterns we got it. From this spectrum we need to, and this is a convoluted data. So here the resolution is 0.7 electron volt. So here this is the convoluted data. You have to do the deconvolution process. Once you do the deconvolution process, then you will find what are the chemical bonding happen in your materials. Like whether the carbon bonded with carbon, it's from the advantageous carbon, or the carbon bonded with oxygen. So those information you have to do that from the deconvolution process. So this is the oxygen spectrum and this is the carbon spectrum. So the direct information is here you have one pattern or one spectrum, and here you have one spectrum. So here you have to do the deconvolution process and you have to denote whether carbon. So for that the Thermo Fisher Scientific, they have given one database from the knowledge view. So here we are using the knowledge view. So here you have to select which element you want to check. So this is nothing but this is the references or the database from the literatures. So here the reference, which reference, this data informations are collected from this reference. In 2004 they published articles like that. So they have some data source, from that also you can get some information from this. So for that here we have got this pattern. So this is the carbon spectrum. So this one, and we have the solder peak and we have the hump peak. So when we check with the literature, and this peak position like 289, so then we have the solder peak, it's around 287. Then you have the peak around 285.8. okay, so this 285.8 is not from this carbon bonded with carbon, because the carbon bonded with carbon, like the advantageous carbon, their binding energy scale is 284.8, but this is shifted to one electron volt. So this has to be corrected before analyzing your data. So here you can see from the literature, so this peak position is corresponds to 284.8. So now we got 285.8. This 1 electron volt has to be corrected to the neighbor elements, like what are your materials that also will be shifted to 1 electron volt, that has to be corrected. So first things, you will receive the raw data. So once you receive the raw data, you have to check the carbon peak position. So carbon is the reference. So this carbon deposited in all the materials from the environment. So now this carbon spectrum in the XPS, they are using as a reference spectrum. So you have to check the carbon peak position. From this carbon peak positions, how much EV is shifted, that has to be corrected to your corresponding elements. So once you do the charge corrections, then you have to do the background corrections. So for these background corrections, you can go with a Topard background or this Serli background. It depends on the symmetric and asymmetric nature of your spectrum. And here we are using the Advantage software. This Advantage software is a licensed version and it's separate from the Thermophaser Scientific. So here we are using the combination of Topcard and Serli background, like we call it as smart background. But when you use the PeakFit 4.1 or the CASA XPS, you can either use Serli background or Topcard background. It depends on your material spectrum. Once you do the background corrections, then you can go for the fitting options. So for the demonstration purpose, just I will fix it here. So here we have the peak fitting options. So first we have to do the charge correction. Now this peak position is corresponding to 285.8. So the 1 electron volt has to be corrected in the spectrum. So this is the shifting options. So here 1 electron volt has to be reduced. So now accepted. So here you can see now the carbon peak position is 284.8. So previously it was 285.8. Now it shifted to 284.8 for all the spectrum. So I have corrected the charge corrections. So once I did the charge correction, then I have to do the background corrections. So here we have the options of Serli background and Topcard background, and here we have the smart background. So I have chosen that smart background. It's a combination of Serli and Topcard. So then I have to choose the range. So when is the flat is there, then you have to fix the range where you want to choose. So then you add the background. So now the background is corrected. So once you did the background, then you go for the fitting options. So the software itself, it automatically choose how to fit the data. So now you fix this data, then here you have the reference, then you have to choose this second one. So you have to come from this side, and here I am thinking, I am adding one peak here, other one here. So here this reference also there is no peak, and so from this just go to and fit this level. Okay, then again fit this level, then again fit this level. So now it's fitted roughly. Then you go to the peak fit. So here you have to apply the constraint. So you have to, based on your chemistry and based on your synthesis procedure, what is the chemical compositions can be occurred in your samples, you have to do the constraints. So once you apply all the constraints, the peak, the fitting will be nicely fitted. Then you can denote this 287, it corresponds to carbon, oxygen, carbon, and this is correspond to carbon bonded with carbon. So this deconvoluted data you have to submit for your publications. So the procedures will be the different, but based on the softwares it will be vary. So either CASA XPS, the same, what are the things we are doing, the same things you have to follow for the peak fit 4.1, and here we are using the Avantage software. So once you fit all the data, you have to check the chi-square value. So the chi-square value is here is 73, but once you, the goodness of the fit is reduced, then the fit. So here it's not fitting perfectly, but you have to adjust the constraints. So like you have to adjust this constraint full width half maximum and the tail functions of this Lorentzian and Gaussian fit, then this will be fitted. Okay. Thank you. Okay, sir. So any doubts? So if you have any doubts, then if you have any doubts, then you can post to the convener. We will address in the future. Yes, sir. So thank you all. Thank you for your patience for the first 30 minutes. So I hope you have understand something about the XPS spectrum. Thank you.
Friends, you have any doubt or you have any doubt, any discussion? Okay, we will discuss in XPS lecture. Okay, and if you have anything, you just mail us, or anything you can do WhatsApp, or you can paste in the Zoom. Okay, we will address you all those things. Anyway, day after tomorrow we have lecture on XPS. There you can clarify all the doubts, anything.